Here's problem 3423. A possible means of spaceflight is to place a perfectly reflecting aluminized sheet into Earth orbit and use the light from the sun to push this solar sail. If a huge sail of area 6 times 10 to the 5 meters squared and mass 6,000 kilograms were placed into orbit and turned toward the sun, what would be the force exerted on the sail? Assume a solar intensity of 1380 watts per meter squared. Alright, so we have ourselves a solar sail, the area of which is 6 times 10 to the 5 square meters, and has a mass of 6,000 kilograms. We have some radiation from the sun actually reflecting off the sail, so it's actually imparting twice the momentum it would if it were being absorbed. And we're given the intensity of the sun at this location is 1380 watts per meter squared. We know intensity, I, Cu, so the energy density at this point is equal to the intensity divided by the speed of light. 1380 divided by 3 times 10 to the 8, and that will give us the energy density at this location. 4.6 times 10 to the minus 6 joules per cubic meter. As we said, the momentum in part is going to be twice as much because of the reflection, and hence the pressure is going to be equal to 2 times the energy density. So that's going to be 2 times 4.6 times 10 to the minus 6, and that will give us 9.2 times 10 to the minus 6 joules per cubic meter, but it's the same as newtons per meter squared, or pascals. That will be the pressure. We want to find the force. Well, pressure is force per area. So the force will equal the pressure times the area. And that's going to be equal to 9.2 times 10 to the minus 6 times the area of this sail, 6 times 10 to the 5, and everything's SI units, so what does that give us? .52 newtons. It's a pretty small force, but there's no friction out in space, and even though we have 6,000 kilograms, I'll give it a small acceleration, a continuous acceleration. As the intensity goes down, the acceleration will decrease, but it will still increase in velocity. 5.52 newtons on this solar sail.